One day, I was outside, doing normal human activities like touching grass and listening to birds, when the blazing sun gave me a strange idea. What if I brought my own malloc? So as soon as I got home, I started building. And in this video, I'll show you how I wrote my own memory allocator in pure C from scratch, and how I used to run a real application. Before we start programming, it's important to understand what malloc actually does. The standard malloc function is used to allocate memory dynamically. For example, you can use it to create a dynamic array whose size is only known at a runtime. But because this is C, there is always some problem with memory hiding somewhere. As you probably know, C doesn't have a built-in garbage collector, so managing memory is the programmer's responsibility. For the allocation, C has a special free function. It takes a pointer to a previously allocated memory block and marks that block as free, so the system can reuse it later. And that means I also need to create my own free function. First, I had to choose the names. I remembered the name of my channel and decided to call them pod_alloc and pod_free. But before we continue, let's take a look at how memory allocation actually works. Every process has its own memory space. This space is divided into several zones. At the top we have the stack, which is used for function calls and local variables. Below it we have the heap, which is used exactly for dynamic user data. And this is the part that malloc works with. Below that there are other memory regions used for global variables, program code and other things that are not really important for us right now. In this layout the stack grows downward, while the heap grows upward. And it's better to keep these two zones from overlapping, unless you really want to meet a segmentation fault. Another question is how we can actually use this heap for our needs. We need some way to request memory from the operating system. There are a few ways to do this, but for me the best is mmap. It works kinda similar to malloc. You tell it how much memory you need and it's return a pointer to the beginning of that memory region. But the important difference is that malloc reserves memory inside an already existing area, while mmap asks the OS for a new memory region of the requested size. Now we can use this to write a simple version of the allocator. To free allocated memory we need to know its size. For that I added a mem_block structure with a size field and a data pointer, which points to the beginning of the memory available to the user. In pod_alloc we simply call mmap to request some memory from the operating system. Then at the beginning of the memory region we place our mem_block structure. It works like a header for the allocated block. Later in pod_free we use this header with mmap. Mmap does the opposite of mmap. It releases the memory back to the OS. For this to work, it needs a pointer to the beginning of the memory region and its size, exactly what we keep in the header. After this we can finally test how it actually works. As you can see, I allocated some memory, wrote some text into it and printed it, and works fine. But of course it can't be that easy. Right now this is basically just a wrapper around mmap and moonmap. The main problem with this approach is time. I wrote a simple test that allocates and frees memory, and then compares it with the malloc from C. As you can see, the difference is really big. My allocator is 435 times slower. It's even slower than me understanding hints. Using this in a real program would seriously slow it down. The reason is mmap and moonmap. Every allocation and every free requires a system call. And they are pretty slow. Sometimes they are so slow that you forget why you even called them. To make our allocator faster, we need to reduce the number of mmap calls as much as possible. A common approach is to call mmap once to allocate a large chunk of memory, usually at least one virtual memory page in your system. If you're wondering what page I'm talking about, here's a quick reminder of what virtual memory is. It's a memory abstraction provided by the operating system. Every process gets its own virtual address space, which is divided into small, fixed-size parts called pages. The program works with virtual addresses, and the system translates these addresses to real physical memory in RAM. Because of this, variables in different programs can even have the same addresses. But that doesn't mean they are stored in the same place in RAM. Each address just belongs to its own process virtual memory space. So, with the new approach we allocate one big chunk of memory and then fill it step by step whenever someone calls pod_alloc. When this page fills up, we allocate another one. As you can see, in this example we have 8 memory allocations, but only 2 mmap calls. This is one of those cases where the number doesn't matter, but matters how you use it. To implement this, I changed the mem_block structure a little bit. Now each block works like part of doubly linked list, and I also added a free flag to show whether the block is available for allocation or not. Also, because we now use pages, I added a page structure. It works like another list, but instead of linking memory blocks, it links different pages together. This will come in handy later. After this, I changed the allocator function. Now it searches for a free block with enough space. If it can't find one, we create another memory page. You may notice that if the user asks for only 100 bytes, we allocate an entire page for it, or use a much bigger block. We are just wasting memory. To deal with this, we split the memory block. One part is given to the user, and the other part remains free for future allocations. With this new approach, I also changed pod free. If we split large memory blocks during allocation, we need to merge them back during deallocation. Then the merged block can be reused later. And now we only return memory to the system when the whole page becomes free. So this approach reduces mmap calls too. Well, let's test this with some allocations. And as you can see, it somehow became worse. Now it is 1823 times slower, which doesn't really look like a better solution. With all previous changes, it looks more like a waste of time. But if we look at the number of mmap calls, it becomes much smaller, so that means the problem is not the system calls. After a bit of investigation, I found that most of the time is spent searching for a free block. More precisely, it takes 99.3% of the total time. On one hand, that's good, because system calls are no longer the main problem. On the other hand, now we need some fancy data structure to make it faster. The current version searches through a list of all memory blocks. It has to check each blocks until it finds a free one, so this takes about O(n) time. Looking at this layout, we can see that free blocks are scattered randomly around the page. At the end of the page, there is also some unused space that has not been allocated yet. What if we move free blocks into a separate list? That's where we can quickly get a free block without searching through all allocated blocks. But there is another problem. We need to find a block with the right size. For example, if we need a block of 100 bytes or more, we may have to skip smaller blocks before finding one that actually fits. This can be fixed too. Instead of using one free list, we create 8 of them. Each list stores memory blocks of a certain size category. When a block is freed, it's added to the appropriate list. The benefit is that this is much faster than the previous approach. Usually programs allocate small chunks of memory, so most allocation will fit into one of those 8 categories. Another question is how to do this in code. First, I added free list pointers to our structures. Then I added functions for inserting blocks into free list and removing blocks from them. Now, when a new page is created, its first free block is automatically added to the appropriate free list. I also changed how splitting works. Now, when we split a block, we remove the original block from the free list, give one part to the user and add the remaining part back to the correct free list. And in pod free, I now use the same insert and remove function to keep all free lists updated. At this point, it can already works, but there is always some hidden problem in a low-level program. And this time the problem is not even the program itself, it's the machine where the program runs. Right now, I can allocate 3 bytes and then 4 bytes, and as you can see, the second addresses is not aligned. On some systems this can cause an error, because some processes don't like unaligned addresses. Also, aligned memory is usually faster to read and write. So, to fix this we need to round up the requested amount of memory. We can do it with simple math, but that would be too slow and I need somehow to justify all the time I spent learning bit operators. This version works much faster. We start by adding this to move the number into the next alignment range. For example, if the number is 12 and the alignment is 8, it becomes 19. When we take that, which is 7, in binary it looks like this, exactly the lowest 3 bits. After that we use the tilde operator to flip the bits and create a mask. Finally we use the AND operator to erase the lowest 3 bits. As a result 19 becomes 16, which is perfectly aligned to 8 bytes. Pretty easy as you can see. So, after crawling through the depths of C, we can finally run it. And this version actually works better than all previous ones. Of course, it's still not as fast as the original malloc, but further improvements would be much harder and would probably give us a smaller performance gain. Testing only with benchmarks is boring, so let's see how it works in a real program. For the target I chose Doom. I replaced its original allocation function with my own. I added some logs to track memory usage and wrote a small Python script to visualize it. After playing for some time, everything worked fine for me. no crashes or anything like that. For me, this was a really interesting project, and I hope you enjoy it too. I recommend you trying to write your own allocator as well. It really helps you understand how memory works and improves your understanding of low-level programming. If you enjoyed this video and want to see more, please subscribe, leave a like and write a comment with your ideas or questions. Thanks for watching.